Okay, so hello and welcome to this first session. So strength of materials is actually our subject, and technically it is Mech 131 or mechanics of deformable bodies. It is the preceding subject after your engineering mechanics or the continuation of the statics and dynamics. So chapter learning objectives. So at the end of this chapter, you will be able to compare the scope of engineering mechanics to that of the strength of materials. And of course, we are going to relate to different types of forces. Next, we distinguish the different types of internal forces. Describe material behavior under different types of stresses. Construct comprehensive free body diagram in solving problems. Actually, you have done this in your statics. And also relate to different formulas, variables, and units involved in simple stress. Then finally, of course, we need to interpret and discuss results of analysis of internal forces. So let's start with comparing the mechanics versus that of strength of materials. In your engineering mechanics, you have dealt with the effects of external forces to a rigid body. So let me emphasize that the rigid body here is unyielding and material does not fail, wherein the material are assumed to be an ideal one, so it is not subject of deformation or any yielding. So when we say yielding, it is reaching its the ultimate strength wherein the material starts to deform, or it may be elongation or shortening. It could be bending or it could be twisting. Okay, so we will elaborate that by and by. So in strength of materials, so of course it is the extension of the mechanics, wherein the external forces will have now its external effects on the body. And of course, bodies are no longer assumed to be rigid. And the main interest of this subject is actually the deformation, because uh, in actual, we can no longer assume that the material will not bend, will not twist, will not crash, or it is not subject to any type of failure. Okay, so that is why the subject is termed as deformable bodies. Okay, so the point of interest or the main feature of this subject is more on deformation. So as an engineer, we are designing the structural members to have a tolerable deformation. When we say tolerable, it may deform, but it will not harm the end users or the community or the uh, users of the building or any structure that we intend to construct. Okay, so it refers to the strength and rigidity of the material. So let me elaborate this further into an example here, wherein we have a fulcrum bar. Okay, so a fulcrum bar is actually a tool in order to uh, simplify the work. Okay, because when we lift that weight there in the figure manually without any tool or equipment or machine, it is very difficult to lift that one manually. So we are using here a type of machine or a tool in order to simplify the force, okay, or minimize the force needed in order to lift that weight. So in mechanics, our concern here is just the force, okay. We can do that by just taking moments at F, wherein the F here is the hinge part of the system. Okay, so when we apply P, F will begin to rotate, and then eventually it will lift now W. So our concern there is the force only. So strength of materials, we are going now to investigate the crowbar if it is sufficient enough to lift the weight without breaking or uh, subject to deformation. So it might be that your material is not sufficient enough for the P to lift the weight in the figure. Okay, so that's all about strength of materials. So I repeat, in engineering mechanics, we are just concerned with the forces, but these external forces will have an internal effects on the body, and the material or the body shall resist that one out of this strength, and that is to be expressed by an expression that I will introduce to you in a short while. Okay, so let us consider here a body subjected to external forces, say F1, F2, and F3. So F1 and F2 and F3, when we apply the axiom of mechanics, wherein the body is in equilibrium, so the body will remain at rest. Okay, otherwise it will accelerate to the direction of the resultant. But if we have a condition of equilibrium, the body will stay at rest. Okay, however, those external forces will have its internal effects, or that internal effects will tend to deform the body itself, or it may twist the body, it may uh, stretch the body, or it may cut the body, or it may shorten the material. Okay, so to give you an idea on the type of forces here, let us have an exploratory section of a certain parallel pip. So we have here three different axes. So an axis that is parallel to the member. So when we say parallel, it is on the axis of the body itself. Okay, so it is along the axis of the body. And then if we have here an axis that is vertical, say Fy, and then we also have here Fz, or the Z axis. So we apply here different types of forces, say starting with the x-axis. Remember that x-axis is parallel to the member. So when we have an applied force along that axis, okay, it is either the body will stretch or the body will compress or shorten, right? So a force that is applied on the x-axis would mean an axial force. So an axial force will cause here a normal stress, and a normal stress could either be tensile. When we say tensile, that is the force is away from the body, and then the compression is the force is towards the body. So when we have these two kinds of forces, the effect is, of course, stretching or shortening. So meaning the effect of tensile is stretching, and the effect of the compression is shortening the body. Okay, so that is a force that is along the x-axis, you can see in the figure. So meanwhile, if we are going to apply a couple, so a couple is a moment force along that axis, or the x-axis parallel to the body, it will be subjected to twisting. And twisting is what we call torsion. Okay, it will have a torsional stress on that. Okay, so that is for the x-axis. What if we go to y-axis? So when we apply a force along the y-axis, the effect is a shear stress or a shear force. So remember the term tangential. Tangential force is actually a force touching the fiber. So when we have a force touching the fiber, the effect is a shear. When we say a shear, it is an effect of tangential force. And a tangential force would tend to cut the body along the direction of the force. Okay? Along the direction of the force. And as we can see, y-axis is perpendicular to your member. So when we apply a force there, the effect is the shear force, or it will tend to cut the section of the member. So meanwhile, again, we apply a couple force on that y-axis. What will happen? It will certainly bend the member. So the effect of the couple applied to y-axis will be bending or flexural stress. Okay, so bending force. Same true with z-axis. If we apply a force along that z-axis, the effect is shear or tangential force. And if we again apply a couple on that z-axis, it will tend to bend your fiber. Okay, so what is the orientation of the bending? On y-axis, it will bend along the x-axis. Okay, and then if we have a couple on the z-axis, okay, the z-axis, we have a bending along the y direction. Okay, so you can see that in the exploratory sections. Okay, so as I have said, bending moments for that y and z axis, and then a normal force will have an axial loads, tension or compression, and then a force along x and z will have shear force or tangential force, and of course a couple that is applied on the axis of the member will have a torque or a torsion. Okay, so here is some member forces of 2D rigid frame. You can see that. So shear force, you can see it's vertical when we consider the x-axis, and then when we apply a couple on that, we will have a bending moment M, and then axial force is present along x-axis, which is parallel to the member. So member forces of 3D rigid frame, the same scenario, but we'll just view it on the three-dimensional manner. So these are the type of stresses or simple stresses. Number one, tensional stress, and then compressional stress, and then the shear stress. The shear stress, you can see, is a cutting force, will tend to cut the section. Okay, Anyway, we have learned how to get the components there previously in your statics. When we have shear stress, it is actually a tangential force. It is also, it could also be a diagonal force. So it is not only horizontal or vertical, but it could be a diagonal force. But the two type of stresses here, the tensional and compressional stress, will only have one orientation of force, or the force is along the axial axis or parallel to the member. So for the first topic, this is a condition where stress is constant or uniformly distributed. So it could either be compressive or tensile stress. So do not make it that complicated, because the title itself simple, stress. So it is actually the force per unit area. So in strength of materials, this expression is termed as unit load. So that is unit load. When we say unit load, it is force per unit area, meaning the force will be just uh, be distributed along the cross-sectional area of your member. So it is denoted by the Greek letter sigma. So sigma simply equal to P over A. So in SI units, we will be dealing with megapascal. So megapascal is actually meganewton per square millimeter, or newton per square millimeter. So again, megapascal is meganewton per meter squared, or newton per millimeter squared. So basically, you need to have to recall the prefixes of the units. Okay. So in English units, so let us correct this to be English units, ano. So the expression of sigma is pounds per square inch, or pounds per square foot. So that is in English units. Okay. So now we are going to have some of the details here. So the simple stress are expressed as the ratio of the applied force divided by the resisting area. So just make it simple. This is just equal to force all over area. This is the expression of force per unit area to structural members that are subjected to external forces or induced forces. The external forces are the applied loads. Okay. What is the effect of these external forces? It is actually the resisting forces. Stress is the lead to accurately describe and predict the elastic deformation of a body. So actually, simple stress can be classified as normal stress, shear stress, bearing stress. And the system of units will be just the same for the three classifications of the simple stress. So in SI units, again, it is Newton per square millimeter, or meganewton per square meter. In English system, PSF or PSI. So in US customary, it could be kips per square inches, or KSI. So the normal stress is either tensile or compressive stress. So meaning normal stress is equal to the normal force all over the cross-sectional area. So we can see here that P is the normal force parallel to the axis of the body. So it could be either tension or compression. Tensile force is pulling force away from the body, and compressive force is a pushing force towards the body. So let us put into practice that when we have a tensile force, that will be denoted by a positive. Why positive? Because it is actually stretching the body, so there will be an additional length because of that stretching. But that is not good. Okay, so both waist tension and compression, uh, uh, when we reach a tolerable tension or compression, that is not good, because our intention is to control the deformation, or control the elongation, or control the shortening of the member. Okay, so compressive force is a pushing force towards the body. So we can see here on the arrowhead, so the arrowhead is away from the joint or away from the body for tension. And for compression, you can see that the arrowhead is towards the structural member. Okay, so let us consider here problem number 1. So we have here a hollow steel tube with an inside diameter of 150 millimeter, is to carry a tensile load of 500 kilonewton. Determine the outside diameter of the tube if the stress is limited to 150 meganewton per square meter. So when we say hollow, there will be a hole here, so meaning it is not a solid one. So that is classified as steel tube, or sometimes in most often it is normally a GI pipe, or a steel pipe. Okay, so in order to calculate the outside diameter, we'll just have to use this formula. Say sigma is equal to P all over A. Okay, so before we apply this formula, let us identify the given here. So 150 meganewton per square meter is actually the allowable sigma, or the allowable normal stress. That is 150 meganewton per square meter, or simply it is megapascal. And megapascal should be in terms of newton and square millimeter. So the black area here is actually the area that will be uh, that will absorb P here. So meaning your P will be just distributed along the hollow area here. Okay, so simply we'll just have to apply that formula, 150. Of course, you should be consistent in the units. Remember to express your force into newton and the area in square millimeter. Okay, so your force here is 500 kilonewton. So we need to express it in newton. So remember that 1000 newton is equal to 1 kilonewton. So therefore 500 here is in kilonewton. Okay, so 500 kilonewton, let us apply that conversion factor, wherein 1 kilonewton will be equal to 1000 newton, so that we can cancel the kilonewton units here. So we need to multiply this by times 10 raised to 3, okay, or times 1000. And for the area, so the area for a circular section is actually pi over 4 all over the diameter squared. So in this case, if we have a circular area and the smaller area here, so we'll be just concerned with this shaded portion here, okay. So meaning we will apply this to the larger circle minus the smaller circle. So in short, we'll be having a formula pi all over 4 times the larger diameter, which is the unknown, minus the smaller diameter, which is 150 squared. So if we manipulate that, okay, we just cross multiply that one and then divide this to 500,000. Okay, so here it is. So we manipulate 150 times pi all over 4 times d squared minus 150 squared is equal to 500 times 10 cube. So we are solving d here, so we need to isolate this bracket by dividing both sides by 150 times pi all over 4, so we can cancel that one. So 150 times pi all over 4. Okay, so next, copy this. We can now omit this portion. It's already cancelled. And remove the bracket here. So of course, this will be transposed to the other side. Okay. So transposing that to the other side becomes positive. And then we extract the square root. Of both sides. Then we will come up with the value of the required diameter here. So that your diameter will be equal to 163.54 millimeters. Okay. So that's it for this first problem. So next problem. A homogeneous 500 kilogram bar AB is supported by at either end by the cables as shown in the figure. So we have here a steel cable which is 3 meters in length and a bronze cable on the other side which is 6 meters in length. Calculate the smallest area of each cable if the stress is not to exceed 85 megapascals in bronze and 130 megapascal in steel. So in this case, so we have an allowable stress for steel, which is equal to 130 megapascals. And of course, we also have the allowable for bronze, which is 85 megapascal. So the solution is simple as long as you know what is the actual forces involved here. Okay. So as you can see here, that the scope of strength of materials is only within this formula, P over A. And your task is to determine the internal forces wherein we will now apply our knowledge in your engineering mechanics. Of course, as usual, we are going to have a free body diagram, of course. So if this is the bar has a weight, and the location of weight is located at the centroid or the mid of 8 meters. Say this is the force, and that is 500 kilogram. Say W is equal to 500 kilogram. And remember that W is mg. Okay, g is acceleration due to gravity. So we need to multiply this by 9.81 to come up with a force weight here, and that will be equal to 4,905 Newton. Okay, we also have here P of steel and P of bronze. So solving for P of steel and P of bronze, it is just equal to the half of 4,905, because eventually there is a symmetry here, so we do not need to take moments at this point, take moments at point. It is obvious that P of steel and P of bronze will just share to resist 4,905 Newton, and that is 2,452.5 Newton. So this is by symmetry. And that's it. You can now apply this formula. So we have sigma is equal to P over A. Say for steel, we have here steel. We just cross multiply that one. We have sigma A is equal to P for steel, and area steel is equal to P all over sigma. And by this we have 2,452.5 all over the allowable for steel is 130. So we will have 18.87 square millimeters for steel. So for bronze, we will do the same. So we copy that one and then just adapt the given for bronze. Okay. So P for bronze is equal to this. 2,452.5 divided by the allowable for bronze is 85. So therefore, we just divide that. We have 28.85 square millimeters. Okay, so that's it for this problem. So we'll now proceed to the third problem. So as we can see here, the block is suspended by two cables, namely AB and BC. So AB and BC has different inclination with respect to the horizontal. So the cable areas are also given here. We have 300 millimeters squared for cable AB and 500 millimeter squared for cable BC. So remember that these two cables will fail simultaneously. So unlike on the second problem, they are just equal. So but this time, the value for AB and BC will no longer be equal because this is not a symmetrical configuration. So what is the implication of that? Meaning, we will adopt the smaller value of W derived out of the failure or of either AB or BC. So it cannot be that perhaps you might think that this is the approach here is just simple. Okay, so perhaps you might think that you'll just have to establish by joint or resort to joint method here, and then we have here W, and then this is a tensile PBC inclined at 30 degrees, and then this is PAB inclined at 50 degrees, and then see the given applying this formula P over E. See for AB we have 100 megapascal. By the way, sigma AB, these are allowables, will be just equal to sigma BC according to the problem, that is 100 megapascal. So the capacity of each of the cable is limited to 100 megapascal. Okay, so you might think that out of this given, you can right away determine the P of steel and P of AB and P of BC by simply cross multiplying, because if we are going to cross multiply this one, we'll just have P is equal to sigma times area. So you might think that PAB simply sigma of AB times area of AB, and then just adopt 100 here, and area for AB is 300. Okay, so actually this is 30,000 newtons, and then for PBC we do the same, sigma BC times area of BC, this is 100 times the area, which is 500, so that is simply equal to 50,000 Newton. Okay, so we come up with these two values, and you might resort to summation forces vertical. We'll just have to see that W is negative, and then an upward component of PAB, or the vertical component here, is opposite your angle or your reference angle. So we're going to use sine 50 here, and then an upward force of PBC. Again, your vertical component here is opposite your reference angle, so you'll be having here sine of 30 degrees. So this is equal to 0. So meaning you might have this equation, PB sine of 50 plus PBC sine of 30 degrees, and all you need is to substitute. So you substitute, that's it. You can get the value of W. So that is a wrong procedure. Okay. So the correct procedure will be until this line. So do not ever substitute what you have derived here. Okay. Because again, the failure of AB and BC will not the same. By the value itself, you can see that BC has a greater load capacity than that of AB. So meaning, we are going to adopt a value of W wherein AB will not exceed 30,000 or BC will not exceed 50,000. So let us have an investigation. So where shall we investigate? So an investigation could be done by summation forces X, because if we are going to use this one, it will involve the unknown W, so there will be a lot of unknowns. So unlike on X, will be just involving AB and BC here, because AB and BC will just have to pull each other, okay, along X direction. So writing this equation, equilibrium equation, we have leftwards PAB, that is negative, and the horizontal component is cosine of 50 degrees, plus rightwards BC, the component is to be multiplied by cosine 30 degrees, and this is equal to 0. So we can simply say that PAB cosine 50 is equal to PBC cosine of 30 degrees. So the procedure is this one. We'll have, if PAB is 30,000, what is PBC? Okay, so we use this equation. Say this is we are going to tag our equations. So this is 1 and this is equation 2. So from equation 2, we investigate PAB is 30,000. What is PBC? So the question is, if PAB is 30,000, shall PBC will exceed 50,000? So that is the question. So by using this, we'll have to copy this, place it here, and then substitute. So this is 30,000. Then we can solve for PBC right away. That is 30,000 cosine 50 all over cosine of 30 degrees. Therefore, this is equal to 22,266.82 newtons. So observation is that the derived PBC here is less than 50,000. Remember, the capacity of PBC is limited to 50,000. Okay? That is why we can now conclude that we use PAB, which is 30,000 Newton, and PBC, which is 22,266.82 Newton. So we're gonna use this to compute W in equation 1. Okay. So before we substitute, let us have a condition. What if, I'll just show you, what if PBC is adopted on your first calculation? Say, if you're going to adopt 50,000 Newton, what is PAB? So again, we are going to use equation 2. Okay, just have to copy this equation 2 here, and then substitute here 50,000. So if we're going to do this, we can now derive, this is supposed to be 50,000. Therefore, PAB is equal to 50,000 cosine of 30 all over cosine of 50 degrees. So we can have now the value of PAB equal to 67,364.82. So what is your observation now? So this PAB will be over the limit, because the limit of PAB is just 30,000. So if this is your assumption, then it will go back to this solution. Therefore, use PAB is equal to 30,000, solving for PBC and W. So again, you can appreciate the solution by asking your if you're whether you're gonna adopt 30,000 or 50,000. So in this case, we adopted 30,000, yielding to a lower value to the limit of PBC. Therefore, we're going to use PAB 30,000 and PBC is equal to 22,266.82. So now this is not acceptable in computing W, since AB here in the first place have exceeded the limit if we're going to adopt 50,000 as the initial computation. Okay, so we are going to substitute now the value. Say here we have W is equal to 30,000 times sine of 50 plus PBC 22,266.82 sine of 30 degrees. So therefore W is 34,114.74 Newton. Okay, so this is the correct answer for W. So let me reiterate that the failure, the capacity of each of the cable are unique. So therefore, you cannot just use both of them in order to derive the load here. Okay, so as an alternate solution, since we have here three forces, recall that in your mechanics that you can form here a force triangle. Just follow your angles. So it's basic that you know where to get the angle, whether the vertical one or the horizontal one. So let me have here some angles involved. So 50 degrees on horizontal. The remaining angle here is 40 degrees. Okay. And 30 degrees with the horizontal. The remaining here is 60 degrees to have a right angle there. So if you know all of this angle, you are now ready to draw the force triangle. So all you have to do is to draw an X and Y axis here. Okay. For the first force, so PBC is inclined at 30 degrees with the horizontal. So remember, the reference line you intended to get your angle. So in this case, I'm going to use the horizontal line, 30 degrees. And then we connect PAB here. Say this is the axis. Say this is PAB. So what is the angle? That is 50 degrees with the horizontal. And finally, the weight that is going vertically downwards to close your force triangle. Say this is W. Okay, so this is the force triangle. So of course you need to complete the angles involved here. Say 30 degrees will just be transferred inside your triangle. See, this is 50 degrees. 30 degrees. Okay. And what is this angle? This is 60 degrees. Okay. So of course, PAB is inclined with the vertical with 40 degrees. This is 40 degrees. So therefore, this is also 40 degrees. So PAB with the vertical 40 degrees. PAB with the vertical 40 degrees. PAB, this is PAB, with the vertical is 40 degrees. So finally, you can now compute your first triangle. Say, looks like this one. Say this is PAB, this is W, this is PBC, 40 degrees, 40. So this is 80 degrees, and this is 60 degrees. So we can now apply sine law. W is to sine of 80 degrees. The way this is by sine law is equal to PAB is to sine of 60 degrees. Okay. And then PBC is to sine of 40. So we'll just have to get the opposite angle. This one to that, this one to that, and this one to that. Okay. So here we apply that the limit of PBC is 50,000 and the limit of PAB is 30,000. So we're going to pair each of those to W. Each of the sides W sine 80 is equal to 30,000 all over sine 60 degrees. Hence, W is 30,000 times sine of 80 all over sine of 60. So we have a value for W equal to 34,144.74 Newton. Assuming that we have no idea whether this is correct or not. So we can check that if we're going to pair the other side on it. What if 50,000 prevails? W sine of 80. So we pair this to this side. So 50,000 over sine of 40. So by cross multiplication and manipulation, we have 50,000 times sine of 80 all over sine of 40 degrees. So therefore, we will have a value of W equal to 76,644 Newton. So we can see now the result of two different pairs. Of course, we are going to adapt this one. So we cannot adapt this one we always adopt the smaller value because you know the implication of that. If we're going to choose this one, your PAB will fail. Okay, just as presented on the first solution we had. Okay, so this is the alternate solution wherein we are going to use the force triangle. So I think we are done with this problem. Okay, and as for your exercise for today, I'm gonna leave problem number 4, wherein the cross-sectional area for all members are already given here. So we'll just have to determine the stresses at members BC, BD, and BE. And you're going to indicate the type of stresses, whether it is a tensile or compressive stress. So you know what to do here. So the first step is to determine the reactions and then go over with the analysis of trusses in order to come up with those members BC, BD, and BE. You can use joint method or section method in dealing with the internal forces of those unknown members. Okay, so that is problem number 4. And then problem number 5 also will be your seat work today. So for problem number 5, we can see here that this is rigidly attached to a certain wall. So all you need is to determine the stresses in each of these sections. So you can use here section method in order to determine the actual forces on aluminum, on the steel, and on the bronze. So remember, there will be a restraining reaction here, okay, in order to have the system in equilibrium. Okay, so I suggest that you go over resolving the first 3 problems today and then solve number 4 and number 5. Okay, so see you on the next meeting and we'll discuss this on the next meeting. So thank you for listening.